Hello everyone, welcome back. So our next speaker is Ruth Hall, Professor of History and Philosophy of Science at Indiana University of Bloomington. And from my experience, personal experience, I can say that she's also a great dissertation advisor. Please join me in welcoming Professor Jutta Schickore, and she's going to speak today about repetition and replication in the life sciences historical perspective.
Thanks very much for the kind words and thanks for the introduction, for the invitation. I'm really glad to be here. Okay, let's get the history out of the way. So I'm broadly presenting various historical examples that resonate, as you will see, very nicely with many of the things that we've already discussed. So what we heard already is that the replication crisis became a media trend, and that came with very strong statements that were made about replicability being the gold standard for science. Here's an example from 2012 from the scientist. The gold standard for science is reproducibility. Ideally, research results are only worthy of attention, publication, and citation if independent researchers can replicate them using a particular study's methods and materials. So it's quite close to what Alan Franklin said earlier. So several years, conferences, editorials, and panels later, the discussion on replication has grown quite sophisticated. And I think some of the distinctions that we've heard this morning have become established. So there's the distinction between performing the same experiment several times, so what I will call repetition in my talk, the copying of an experiment in a different setting by different experimenters, or the distinctions that Hans Rader has presented this morning about obtaining the same results through the same methods and obtaining the same results through different methods. And he has already mentioned that in the sciences themselves, usually this is called conceptual replication. Several scientists and analysts of science, this also came out this morning, are concerned that overemphasis on replication arises from a misunderstanding of how science really works. And I expect that we hear more about that from Stuart Firestein. And so the idea is that this overemphasis might actually be damaging to scientific research. So, I mean, it is clear, and it has become clearer this morning, that we need to move away from the grand simplistic claims and offer a more fine-grained account of natures and roles of replications in scientific research. And that's what I would like to add to by taking a historical approach. Now, that can also mean quite different things. There is the history of the term itself. There is the practices of replication or repetition that also have histories, as I think you will see soon, and also the scientists' views on replication. So the question of whether it is in fact a gold standard, or considered to be a gold standard, that also has an interesting history or histories. So this is another distinction, I think, that we need to keep in mind, the different ways in which we can look at this in historical perspective. Now, I don't have a lot to say about the term. I just did a quick and dirty Google Ngram, and there's something interesting here in the sense that what is suggested here is that prior to the 1960s, the word replication comes up mostly in the legal context. So when you look up the references that are provided through Google Ngram, what you find is that it is usually used in the context as a plaintiff's reply to the defendant's plea. That's a replication, which I thought was an interesting find. I didn't really do much work with this, but it would be interesting to see when this went into the sciences, at what point. And then, of course, from the mid-20th century onwards, we have the replication in the context of molecular genetics as DNA replication. And that's, I think, what accounts for most of the steep increase from the 1960s onward. But what I want to do in my talk is I want to look at practices and also at the history of scientists' views on replication. So my questions will be, did past scientists redo each other's work? Was it a very common practice? Were they aiming for reproducibility or replicability in Hans Otter's sense? And I will also ask the related but distinct questions, how did they view replication practices? What the significance did they attach to replication? And what you see here is the first programmatic text that I want to begin with. I will have two programmatic texts from the early modern period, and then I'll go on to look at some specific examples of actual experimentation projects. And then hopefully I'll get to some lessons from all this, and we can do more of that in the discussion. So what we see here is a text. It's actually a collection of essays from the mid-17th century. Robert Boyle was also mentioned already, a natural philosopher and member of the Royal Society, who wrote two essays of unsucceeding experiments. And that was at a time when he himself had done and witnessed a number of experiments. And when he said unsucceeding, it meant that an experiment did not produce expected effects. And then he goes through the reasons for that. So that might be a cognitive reason, like the investigator's fancy or imagination that misleads him. But more often than not, the problem was what he calls the unskillfulness of the triers of the experiments, so the lack of skill of the experimenter, and the particular mistaken properties of the materials employed about them. So he was doing a lot of chemical experiments at that time, so he was worried about impurities of the chemicals that he was working with. But then there's also the last on the slide, which is the contingencies to which experiments are obnoxious upon the account of circumstances which either are constantly unobvious or at least are scarce discernible till the trial be passed. So that's quite an interesting thing. The contingencies and accidents that might somehow impede the experiments that you are doing. So for Boyle, he says, he has in a way a very Aristotelian view of that. He says, well, these contingencies or accidents cannot be discoursed of in an accurate method. So you can't really have a methodological account or approach of accidents or contingencies. And you can't even have a systematic treatment of those precisely because they are accidents and contingent. So he gives examples. So he talks about chemists and impure chemicals, gardeners and anatomists who had to deal with the variation in plants and dissected bodies. Physicians were faced with variations in their patients' constitutions. And in fact, everyone had to be aware of what he calls wantonness or deviation of nature. So nature is in fact sometimes very unfriendly to the experimenters. And then he says that there are things that you can do. And what you have to do to deal with these issues is you have to try experiments very carefully and more than once. And especially those which you want to build on. So if you want to build a theoretical superstructure on experiments, you have to make sure that you do them more than once. It is very unsafe to rely too much on single experiments. And then he says, well, a cautious experimenter who performs experimental trials repeatedly has a good reason to be confident in his results. So that's Boyle. When we go to the Italian context at the same time, no, that's what I wanted, we find something interestingly similar and also interestingly different. So that's another academy, the Cimento Academy in Tuscany, also an academy like the Royal Society. And they actually have only one big publication that they published. But it is quite interesting because it also has a programmatic statement in the introduction. And it also has this motto, which you may be able to read, provando e riprovando. So trying and trying again on the title page. So it first looks like very much like Boyle, but the interesting thing is that there is a different twist to it. So in the introduction of that text, we read, besides trying new experiments, it's not less useful to search among those already made. So it has been the aim of our academy to make them on those things that have been done or written about by others. So the Italian academicians insisted that the claims of ancient authorities need to be checked and checked again. So when they say try and try again, this is really what they have in mind. They are talking about the ancient authorities and the results that they have produced, and that we have to be critical and try to redo this and not take it for granted and not just, buy what the authorities tell us. So they seem to be saying the same thing at first, but when we look more closely, it's a slightly different way or a slightly different reason for why we have to redo experiments. They emphasize excessive trust and reverence for a name should not keep us from checking other people's results. So now I want to give you a couple of examples from that context, and that's where the snakes come in. So this is about the ambiguity of notions of repetition or imitation, as it was called. So the context for that is a series of experiments that Francesco Redi was doing. He was a member of the Cimento Academy in the 1660s, and he studied the nature and working of viper venom. And so he advanced two things. First, that the yellow liquor that comes out of the viper's teeth causes the fatal consequences of the snake bites. That was, in fact, something that was critical of the ancient position because it was assumed that it was the bile of the viper that was actually deadly. And Redi also said that this kills only when you put it in wounds. So when you ingest snake venom, it doesn't do anything to you. And he presented a number of experiments to support that view. And then he has this critic that I will also talk about, the French critic who comes to quite different view and advances a quite different idea of the function of viper venom. So, what is interesting, there are many things that are interesting, but Redi begins very explicitly with a wish that he wants to refute old fables about vipers. And like Boyle, he states that he will not trust the phenomena if they are not confirmed by iterated and reiterated experience, so you have to make the experiments many, many times. He says he had observed very often that the yellow liquor spurted into wounds when vipers struck. The effects of the yellow fluid were tested on many animals, and he had demonstrated the effect of venom taken from dead vipers in more than 100 experiments. So it's always the emphasis on, I did it many times, I did 100 experiments, I used many animals, and so on and so forth. An interesting thing is a comparative trial that he did where he punctures the thighs of pigeons, again 10 pigeons, not just one, with a broom straw, which was dipped in viper venom, and then he left the poison straw in the wounds, and all pigeons died. And he also wounded 4 other pigeons, again 4, not 1, with straws that had not been dipped in the fluid, and these birds survived. So that shows that it really is the venom and not just the wound that is fatal. And he demonstrates that in all these poor pigeons and rabbits and so forth. So his critic had a different idea. He says it's not the yellow liquor, it's the rage of the viper. So the mental state of the viper, that is actually the cause of the death of the animal. And so he had a different task. When he did his experiment, he had to compare animals bitten by angry vipers and animals bitten by happy vipers and see whether that actually makes a difference. And that was what he did, and he demonstrated that, in fact, only angry vipers are deadly. Well, I think the idea was that they are happy by nature, and then you prod them, and then you make them angry. So I think the natural state of the viper is that it's actually quite content. So the interesting thing for this context here is that both of these people stressed the importance of repetitions of experiments. So we've already seen really emphasize many experiments and also and so on. And he also provides justification. Again, that has to do with what I said earlier about the accidents. He insisted that oftentimes it happens, I'm quoting, that genuine causes for some unknown or unseen hindrance cannot produce their effects. And he gives examples from his own practice where his own experiments had been frustrated by impediments or accidents, and some he could identify and some he couldn't identify. And then so he says that sheep or dogs and cocks were bitten by vipers and survived. They did not die, and he also had a bird die from the bite of a viper whose venom had been removed, which also didn't fit his theory. And he insisted that only by performing experiments repeatedly could you really make sure that all these accidents were excluded. Shiraz also emphasized repetitions. But what is interesting is that when you look closely, they disagreed about the meaning of many, many experiments, which to us seems to be, this is an obvious thing, many, many experiments. Well, you just repeated many times. But interesting thing is that when Shiraz says that what he means is that he and his group had made lots of experiments. Just, it doesn't necessarily have to be the same thing, but just, they did many on all kinds of issues related to this. So there's an interesting vignette that shows this different interpretation. So he had one experiment where he had made a viper bite 5 pigeons consecutively, and all had died. And then Redi, in his response, said, well, you have to do more trials. And Shiraz, and that surely meant that you have to do the same thing. So you have to take a new viper and have it bite another 5 animals and then do it again and so on. And Shiraz took Redi to mean that more pigeons should have bitten by the same viper. And he just didn't see the point of that, because Redi himself had found that the yellow liquor was exhausted after the first and second bite. So why repeat that? And so Shiraz said he had done more than enough to maintain his reflection. So when we look at that, we can distinguish at least 3 different meanings of what it means to do an experiment many, many times. So it's lots of experiments, a large number of experiments from many different angles. many repetitions of a particular trial, or enough trials for a specific purpose. And actually more than enough. So one thing, I'll say a little bit about more than enough in a second, but one thing what we see here is then when experimenters agree about the importance of repetitions, they could still disagree about how many repetitions were necessary and why they were necessary. So, replication. It is actually quite rare that early modern experimenters refer to genuine replications. So I try to redo your experiment. They call it imitation. And if they do refer to this, then it's really not about replication in our sense of the term, but it's a negotiation of proper procedure. And we had examples for that earlier as well. So those two guys also experimented on the therapeutic effects of viper meat. Schickhore's experiments show that when you swallow a viper head, it was a very effective treatment of snake bite. So he reports that an animal bitten by a viper could be cured by feeding it the head of another viper. Redi reported that he had fed viper heads to two dogs, one head half cooked, the other one crushed, as per Schickhore's description, and both dogs were subsequently bitten in the ear and both survived. Now that's great because it seems that the imitation of that experiment was successful because it confirmed Schickhore's finding. And then Redi said, well, a doubt arose in me. And then he repeated the experiment without feeding the dogs viper meat, and both dogs survived. So from that, he then proceeded to feed viper heads to 2 cocks, 2 dogs, 8 more cocks, 2 kittens, 2 hares, 6 dogs, and all animals died from snake bites, but they were not bitten in the ear, but they were bitten in either the tongue or the thigh. And that is interesting, so because he says that this is the case, and he did even more than Schickhore's. In some trials, the place of the bite had also additionally been smeared with viper blood as an additional antidote. So he had done more than Schickhore's because he gave more antidote than in the original experiment. So it's an imitation, but you do more. And with that in mind, when you read through many of the descriptions of the so-called imitation, this is something that you find very, very often, that the experimenters at the time say, oh, I imitated that experiment, but I did more. So Schickhore's cast doubt on Redi's conclusion and pointed out that Redi's first results had agreed with the evidence obtained by himself. And then he also presented a case history in his favor, where a young man was bitten by a viper while trying to hold it, and the young man had so much faith in Schickhore's that he immediately decided to eat the head and neck of the snake. And Schickhore's served the broiled head, the neck, the heart, and the liver. So he did more. The young man also swallowed some volatile salt of vipers, and he recovered nicely. Even though, as Schickhore's emphasized, the wound had been really, really deep. Schickhore's group also imitated Redi's experiments with the yellow liquor and failed to, where am I on my slides here? They failed to obtain the results that the Italians had obtained, and he gave yellow fluid to pigeons and to kittens, and did more. Namely, he engaged a person who was favorable to Redi to do the procedures. So he said, he told this person to make the incision and said, oh, the gentleman severed the animal so much that he could not hold to tell him, smiling, he did more than Signor Redi himself said his letters had done. So again, he did a deeper wound, he did more than in the original experiment, and lo and behold, no animal died. And on the other hand, when you wound the birds with freshly cut heads of vipers, they survive, even though Shiraz had proceeded by thrusting the teeth into them as deep as he could. So again, he did more than he should. So the evidence of these experiments clearly showed that Redi was wrong. Said Shiraz, he was unable to comprehend why Redi's animals had died after the application of yellow liquor to wounds. So we have here different strategies related to imitation, in the sense of performing the same procedure somewhere else. Typically, imitation is explicitly discussed when something is not working. We also had this morning. Either when different results are obtained or when the results obtained do not fit one's own theory. The researcher who does the unsuccessful imitation typically claims that his experiment yields the correct result. The other researcher's experiment has a flawed design or some unknown factor interferes. And to make the point more forcefully, critics stress that they are not doing the exact same thing, but they are doing more. They are using...
Well, experts in replication, maybe you ought to take a vote on who's right.
So, using more venom, make a bigger wound, and so on. There's a lot more, obviously, that one can say about all this, but I wanted to move on to talk about a slightly different episode from the late 18th century, so 100 years on, which is, it's interestingly different, as you would see. So it's about microscopy, it's about a replication, I suppose. 1870, Alexander Monro, professor of anatomy at Edinburgh, made a very surprising discovery about the microscopic structure of the nerves, which I will show you in a second. The Italian Felice Fontana tried to redo these observations and failed. So here's what Monro finds. He found that the brain and nerves in all classes of animals, in place of straight fibers, are everywhere composed of convoluted fibers. He found these convoluted fibers everywhere in the body. That's what this plate shows here. You find on the left side the examples of various different tissues and other materials that Monro looked at. And this small picture here is something that I enlarged. So they all show these wiggly worms that you see there. So when you look closely at the plate in the volume, you see these wiggly worms everywhere. And so he found that in the nerves, and then he starts looking at other tissues, and he finds it in the entire vegetable kingdom. And then he says, well, it's also in the metals, in the semi-metals, earth, salt, they all consist almost entirely of convoluted fibers. So this was really a sensational discovery because it meant that there was a universal elementary structure common to organic as well as inorganic substances. So, I mean, this was really something big. So Fontana got really energized by this and tried to redo this and tried to make the same observations. And he said, I examined the matter as if it was entirely new to me, and began his observations with lenses of low magnification, of 6 and 8. and found something which was quite different from Monroe's observations, which you see on this plate. He found, not the wiggly worms that we just saw, that he found that the nerves were covered with spiral bands that were wound around them as a ribbon would do around a cylinder, which you can see in the upper left-hand corner. So, and the interesting thing is that that in itself then did not set off a controversy, but for him it was an occasion to look even more carefully, to pay attention to the conditions of observation and to vary his procedures. So he started fiddling around with the microscope, with the illumination, with the object, and so on. And then found something interesting, namely with larger magnification, the spiral bands disappeared, and they seem to consist of parallel winding fibers. So now we have three structures. We have the wiggly worms, we have the spiral bands, and then we have this, which is, you know, like wavy structures. Now the question is, what is right? So he begins to change the magnification, the illumination, the angle of the light rays, and so on and so forth. And finally finds that the problem is caused by the illumination, and that he could make the bands and fibers appear and disappear by throwing more or less light on the object. And he stressed that he had done so, and he'd done numerous repetitions, numerous variations, and described in quite detailed fashion how he did that. So he listed all the circumstances, how they varied between the observations. And what's interesting is he also presents a plate with all the results. So with the spiral bands, the wavy fibers, and then the lower ones are actually comparing how the effects change when you change the illumination. So then you move from figure 10 to figure 11. So that's really at the border where things seem to change. So now, of course, it is likely that Fontana also described these details of his own observations because he wanted to make sure that others could replicate them. But what I find interesting about this case is really that initially the fact that he was unable to replicate Monroe's observation did not mean even anything conclusive even to him. It was an occasion for him to probe the various conditions of both Monroe's and his own observations. And in the end he found that the correct structure was something yet different, namely this wavy structure. And I mean, needless to say, in the long run, those findings were also cast aside. So, historically oriented discussions about replication tend to focus on path-breaking events. I mean, there's the big book on Boyle's research with air pumps, there's Shapin and Schaffer, there's Newton's prisms, Schaffer and Shapiro, there's, of course, Weber's work on the gravitational waves, Franklin and Harry Collins, where the stakes of their replication are really high and the entire field is affected and impacted. But what I found so interesting about these examples is when we look at more humdrum research contexts, we will find that these so-called replication crises are quite common and a motor for the advancement of methods and techniques and, I guess, also of knowledge. So around 1800, many scientific fields began to expand, including microscopy, by the way. So more and more people began to pursue investigations, quite similar investigations, and they come up with very different results. So what we found here in the cases that I've described is two people arguing, both in the 17th and then also in the 18th century. And what I just showed with regard to the microscope is something that seems to happen on a larger scale throughout the 19th century. It's not two people arguing, but many people arguing. So, for example, agricultural experiments around that time, early 19th century. We see a number of agriculturists doing field trials to figure out how to improve plant growth, obviously a big economic problem at that time. So, to improve plant growth, increase yield. They compared the efficacy of cow dung, plant dung, mineral fertilizers, such as waste from salt mining, or quicklime, or bone meal, or burnt clay, which is an interesting one. And they just want to figure out what happens when you put that on the field, do the plants grow better? And so what you see is several agriculturists trying to reproduce other people's trials, and they have very little success with that. Just a very brief example that I pulled up from the English agriculturist Beetson, who found that burnt clay is really beneficial to plant growth. So when you put that on the field, as he says, you have really huge success. So he did that, had 4 burnt clay experiments, around which was a space unmanured, and then he compared that with wash dung. Clay experiments, he said, maintained a very striking superiority during the growth of the 3 successive crops. The 4 experiments were all greatly superior in produce and perfectly clean and free from weeds, whilst all the dung part was absolutely choked with knot and other grasses, and vastly inferior in produce, although the pole had been twice sowed during the growth of the crop. So dung is actually a lot less efficient than burnt clay. Now, when some German agriculturists repeated this, they did not find the effect. The field trials of Lampadius, for example, showed that burnt clay was less than half as effective as dung. So that clearly contradicted Beetson. And the agriculturist Gustav Schübler comes to yet another conclusion about the roles of minerals. He suggests that they actually change the physical property of the soil, and so depending on what soil you have to begin with, the burnt clay has quite different effects. When you fast forward to the late 1830s, you have an academy posing a prize question on are mineral plants necessary components for plant growth? And then there was the side issue also, is the plant actually able to make minerals itself, or do they have to come from the outside? And never mind what came out of this. This was, of course, yet another result. But what I find interesting is that you have here exactly the same dynamics. So you have not 2, but you have several people doing the same experiment. You come to these vastly different results. And then you kind of have this moment of reflection, where in this case the prize essay says, well, the available literature is confused, it's contradictory, experimenters do not pay enough attention to the circumstances that impact the trial outcomes, and then he has all kinds of things that you have to do. So you have to pay attention to the circumstances, you have to have artificial test soil, you have to have chemically pure test soil, so make sure no organic residues are in there contaminating your experiments, precise controls needed, and so on and so forth. And so this is, I think, really similar to the Fontana case, only, as I said, on a larger scale. The field trials are obviously much more complex, and you have all these different people involved. Many people become interested in this topic. The experiment outcomes become more and more diverse. People become more attuned to the details of their experiments. They begin to examine on the conditions of the experiments, just like Fontana did. And at the same time, they become ever more critical of their predecessors who did not pay enough attention to these details. And I mean, actually, 19th century microscopy is really a treasure trove for these kinds of episodes. So there's, I don't know, some of you may know, there's a huge discussion at that time about the so-called globule hypothesis, according to which organic tissue consists of these tiny globules, and when you look at the description, they proliferate. So they are perfectly spherical or perfectly regular, or they are actually grainy, or arranged in strings of beads, or they originate from fibers and what have you. So there's a whole range of these kinds of descriptions. Blood globules are actually, I don't have pictures of these globule hypotheses, but there are pictures of the blood corpuscles, which I also find remarkable. This is from a handbook of anatomy from 1834, that they were actually depicted next to each other. So the handbook doesn't say, oh, this is the right one. It gives us a whole range, so all these figures are from different individuals and what they saw. So they are actually presented as, well, this is where we are now. So we have all these different descriptions of blood globules, and I mean, blood corpuscles, they had different names for it, so corpuscles, globules. When you look closely, you see that they're also different in shape. Some are round, some are flat, and so on. So this was not presented like that to show that the microscope is actually a really bad instrument and not very reliable. It was presented as a problem for further research. The same happened with test objects for microscopes. That's another nice one. So from the mid-19th century onwards, diatoms with very delicate patterns were increasingly used as test objects to compare the performance of different instruments. And then, of course, you can imagine what happens now, something very similar. So many people use these test objects, and they all describe the patterns, and here you see some, that's the one particular diatom that many people were using. And the more people used it, the more descriptions you get, whether, you know, these are actually elevations or depressions, or what exactly the pattern on this thing is. And then you get, I mean, many, many more papers describing the true pattern on the diatom. So we find that there are countless examples for that. When a group of investigators seeks to establish a certain thing, that you find groping and scrambling and competing assumptions, and they all get published. And then you always find somewhere this moment where somebody said, well, wait a minute. And then they become, they pause, they become reflexive, and they turn their attention to the conditions of experimentation. So I already showed you the prize essay, the methodological caution in agriculture. Then in the case of blood, it was actually the at the time really famous, well-known anatomist and physiologist Johannes Müller, who said, well, we have to see that our microscopy of blood becomes less confused and less contradictory, and we have to really concentrate on how these experiments or observations were produced. In the case of diatoms, this is a really nice quotation. You see in the middle, he's a fellow of the Royal Society complaining that so far from there being any uniformity of statement, we may almost say, well, basically, whoever wrote on this thing has a different description, so we have as many descriptions as people who are working on this. And again, this then leads to a more systematic study of how to establish the pattern on the diatoms. So in the 1940s, we have microscopists using the electron microscope for that purpose. Unfortunately, it also didn't clarify the issue because, I mean, first of all, the electron microscope patterns were not clear enough to settle the issues. And the second, which I find more intriguing, is that at that time, actually, the electron microscope had also needs for test objects, but of course, diatoms were not really very useful for that. So they had moved on to new classes of test objects and had the same problem on a different level. They might be able to solve that diatom problem, but it was no longer the problem that they needed to solve to be able to do these kinds of experiments. So new kinds of tests were needed, and they posed the same problems and difficulties as these pesky diatoms. So, I guess, okay, now I'll include this. We can decide whether it counts. But I wanted to talk very, very briefly about organic analysis because the issue of standardization also came up earlier. So let me just say that this is another nice example for the dynamic that I have outlined. So, for those of you who know a little bit about the history of chemistry, so one of the big advancements in late 18th century chemistry was Lavoisier's new analytic technique of elementary analysis. And he built a very complex and very costly apparatus for that. That's actually another thing that we that somebody who knows more about this than I do could look at in terms of replication, because, and I think actually people have done it, but the problem is that it was very, very difficult to replicate because the experiment was so complicated, the apparatus was so complex, and it was so costly, so not many people did that. And it was something that got established in spite of that fact. Many practitioners just didn't go down that route, and standard history has that Justus Liebig's Kali apparatus in the 1830s kind of removed that problem because he was able to provide an apparatus that made elementary analysis really reliable, because it was you could use it to do this on a large scale and could have a very reliable way of analyzing various substances. And he actually promoted this technique, Liebig did, by putting numerous students through his lab. So this is why some historians of chemistry describe him as a chemist breeder. So he just produced the people who have the skill to do that. But when you look more closely at the time in between, you can see something quite similar to what I've described so far. So there are all these different apparatuses that pop up at that time. People trying out different approaches, developing quite different apparatuses to do the same thing. And what's funny there is when you look at the way in which people promote these and describe these, you find exactly the same reflections. So first there's, oh my God, we have diverse results, so evidently they have something to do with the modes we are operating, so we have to look at this more carefully. And then in the 1830s, there are various ways of addressing that problem, and I just wanted to draw your attention to the last of this, because that guy actually says, well, we should take advantage of the fact that we have so many different strategies and apparatuses and see how the different analytic methods that we have can serve to kind of support one another, so that we have these different techniques that can be used to mutually confirm results of our analysis. So that is as far as I know, one of the few moments where we have a very explicit endorsement of that strategy, that so the reproducibility, I guess, in the distinctions that we had earlier. That where we actually have somebody, a scientist writing, not a very prominent one, I might add, writing that in a paper saying, oh, you know, we should take advantage of this. Yeah, that's maybe something we can talk more about in the discussion. And now, I wanted to reassure you, because when we think about all the lessons, we may find it comforting that there are actually examples of failed trials and successful replications in the literature, so they are getting published. So this is an example from the Journal of Applied Behavior Analysis from 1974. This is the unsuccessful self-treatment of a case of writer's block, as you can see here. And also this is from I guess this is psychology. So this is a failed experiment that actually got published. And I wanted to show you also the reviewer's comments. They praise the author for the brevity, while at the same time emphasizing that the paper contains sufficient detail to allow other investigators to replicate Dr. Upper's failure. So that is very comforting, and it got replicated. In 2007, the failure was successfully replicated, and as you see, the paper is even shorter. The reviewers enthusiastically recommend acceptance, noting that the consistency between the findings of this multi-site cross-cultural replication by Didden and al. And those reported in Upper's now classic paper on writer's block are remarkable and serve to substantially extend the generality of Upper's findings. The consistency between the editorial opinion of the action editor, whose reviewer comments are enclosed verbatim, here, and this paper is quite remarkable. This kind of symmetry is rare in any science, and particularly rare in behavior analysis, and because of it I was compelled to accept it without revision. Another virtue is this awe-inspiring brevity. It's my hope that I will one day serve as the model for brief reports in the Journal of Applied Behavior. So, what else do historical episodes tell us? I think various things. They can help rethink our interpretations of replication and replicability and sharpen our understandings of terms of practices. And I've put together here on the slide some of the things that I find noteworthy about the various episodes that I presented. So there's a long-term history, as we can see, to some of these practices that we've been discussing. And so one of the things that I wanted to argue about the 17th century is that it is really, the emphasis is really different, because there the people are concerned about repetitions and repetitions of their own experiments. And that is really the issue that people are concerned about. So it's about stabilization. It's a key strategy in the late 17th century, but not before. Boyle and Redi put so much emphasis on these strategies because it was a new thing at that time. Also, I think prior to the mid-20th century, we won't find many instances where scientists explicitly endorse this conceptual replication. And this is why I was so struck by that finding that I just showed you from the chemical context, where somebody explicitly calls for something that we might identify as conceptual replication. And I think our conference organizer can tell us more about the history of the strategies. He wrote, after all, an entire dissertation on that topic. But it is really not easy to find these kinds of examples prior to the 19th century where we have people actually explicitly endorsing it. We can talk about the reasons for that, perhaps. One other thing related to that is that the historical episodes can also help throw into relief the differences between the organization of past and present science. So things like nowadays the ubiquity of statistics, the publication pressure, the new reward system. The next speaker will talk about this more. And we can even see in what I presented that even between the 17th and 18th and in the 19th century, the ways in which science was organized, how many people did certain things, how important it was, whether a problem was important or not important, or economically important or not so important. I think even in the examples that I've presented, we can see something like a historical trajectory. And finally, we may take comfort in the fact that replication attempts, broadly understood, were very common in past science and often failed. Observational or experimental phenomena were described in journal articles, then examined by other researchers and found irreproducible. Replication crises or diversity of results were not surprising. They were an occasion for methodological reflections about accidents, circumstances, and sources of error in experimental science. And note that the debates I discussed, so debates on the nature of snake venom, structure of nerve, patterns on test objects, efficacy of fertilizers, were never really brought to a close. Rather, the research field moved on to sophisticated techniques of biochemical analysis, higher resolution microscopes, the fertilizer industry, and so on. And the debates about methods and techniques that were stimulated by the diversity of research outcomes were a driving force for this advancement. Thank you.
You can open the floor for questions.
Is there the possibility that paper on failure of self-treatment for writer's block is a joke? After all, the author is writing about the failure to solve writer's block.
Of course,
it's an inherent contradiction in what he's written.
Of course, it's a joke. Yeah.
So, I mean, it's hard to use jokes as evidence.
No, I wasn't planning to use it as an evidence for anything.
So this is somewhat orthogonal to your main interest, but I'm curious about when people started seeing replications as a source of something like statistical advantages when you're looking for averages and calculating uncertainties. So I know in the 17th century in astronomy, people like Hevelius would report the best results. So they'd have a series of measurements and they'd say they'd have a series of measurements, but they still sort of isolate the one that they thought was the best of the ones they reported. And Newton was unusual in using averages, but I don't know when it became common to use averages, and I don't think it would apply directly to the cases you were looking at, because I don't know how you would average over the deaths from venom. That would be one reason for trying to increase your sample size.
I mean, the specific examples, the explicit call for something like that comes in agricultural experiments, interestingly, from Gustav Magnus, who, after all, is the founder of the Physical Society in Berlin, who actually was involved in these kinds of agricultural experiments also. And he brings these kinds of considerations into the agricultural experiments. I know from a great paper by Jit Buchwald, who looked at the average and the history of the average, that this really only became an issue in the early 19th century. And there are huge differences between the disciplines because in the more quantitative disciplines, I think it got accepted a lot earlier, not surprisingly, whereas physiologists, for example, throughout the 19th century were very cautious, and some were actually also extremely against using these kinds of methods or using statistics in physiological or medical contexts.
So Jackie, on something.
Thanks very much. I really enjoyed that. I had a question about. I had a question about the example that you gave where one scientist was advocating for diversity of methods versus standardization. I was wondering how that response was received by scientists at the time, if you know, or
yeah. I don't think that this was specifically discussed at the time, and this is in part why, I mean, we have kind of been arguing about that or thinking about that for quite a while, and there are not many examples of discussions about that. And it's even hard to find examples for people explicitly calling for this kind of practice. I mean, you may find examples that looking back can be constructed as what we may now call conceptual replications, but an explicit discussion about that as an actual strategy, you know, if you have examples, let me know. I still haven't found very many, whereas the other things, so repetition, variation, and these kinds of things are being discussed in a more abstract, detached way throughout these centuries.
So, so just as a follow-up, in those instances, though, would you say, I mean, are they bona fide conceptual replications insofar as they're all replicating the same thing? Or are there different things being replicated? Like, what are the criteria for determining whether or not they're replications of the same thing?
Well, that's exactly what is being negotiated, I think. So what I find striking is that it really, you always have the feeling that each episode that I looked at, that people are in a sense reinventing the methodological wheel to an extent. So they start out with a problem, and then suddenly many people get interested, and that I think is really a more 19th century phenomenon, because you have more people doing this kind of stuff, and not just this one, you know, exposed person or maybe two, but you really have a community of people who become interested in these problems, and then you have this dynamic that suddenly people say, well, we have this and that and all these differently shaped blood corpuscles. Now, are they in fact all blood corpuscles, or what are we looking at here? And so this is always, you can, I think most of the time you can find this moment where it then becomes reflexive. And then, of course, there's both. Well, what are people actually doing? And, well, is this actually part of the things that we have to understand, or is this something else and belongs somewhere else?
Thanks so much.
So, Hans, Richard, and then Stuart.
And so, also about this conceptual replication example. Of course, a famous case is, say, Jean Perrin in Turkey with all the,
I defer to my colleague.
ways to test avocados hypothesis,
Yeah.
but maybe you want also to have earlier examples.
Yeah.
It's just a guess. I thought, could this Brunner was in 1832, you said,
Yeah.
could it be related to Wilhelm?
Could it be related to Wilhelm Ewell's ideas about the consilience of induction that probably were about the same time? It's just a guess on my part.
I refer to Florian.
It has already been called.
I don't know.
You don't
We
think so?
can discuss it later.
Okay, so it was just.
I agree with him.
So, Richard. And
So,
then Stuart.
the theme in your talk related to some of these questions is trust. That is, these early on, before methods and measuring instruments are fully trusted, people explore the boundary conditions a lot more. And then as we get to trust the methods and the measuring instruments more and more, we just rely on them and we don't explore the boundary conditions very much. And that's sort of good in one way, but then the downside is we begin to only see as far as the end of our nose because we get tunnel vision and only explore what we already have explored before. So there's sort of two sides of this issue. I sort of saw some of that in there. So,
Yeah, there's certainly some of that in microscopy, especially with the test objects. There are also complaints then later on by people who said, well, they are trying to standardize and identify whatever 3 test objects that every microscopist should be using. But what happens is that every microscopist has his, it was mostly men anyway, own test object that he is really familiar with and he can use to compare different instruments because he knows what it's supposed to look like. But then somebody else has a completely different test object that, so it's a push towards standardization with the opposite result in a way. So if there's anything, you would standardize your own thing, but not what everyone else is doing.
Stuart and then Nathan.
So it seems, just from the way we talk about it, that in order to get a positive result accepted, in this earlier work, especially the statement of work, you would replicate or repeat it several times. But to show that it failed somehow or another required fewer times. That is, the experiment had to fail fewer times to say this was a failure. And I just wonder, and that intuitively somehow makes sense, but I wonder if you examine it more carefully, if it really does make sense. There are lots of ways to fail, failing, as it were. Right? And so the failures really should be done just as many times as the successes, if you really consider that a replication. But I don't think we maintain that standard even today.
Yeah, and I don't even think that, so especially for the early modern period, it seems that there's a really, what people actually did and why certain things got accepted and the way in which they presented their strategies are really two different things, and they are not always going together all that well. So, but I've never really looked at it from this other perspective, but I cannot think of an example where somebody said, oh, it failed hundreds of times. At least not the same thing. I mean, there are examples of people who said, oh, I tried so many things and they all failed. But that's, of course, a different sense of many failures.
Do I need the mic?
Just yell.
I liked what you said about kind of diversity of methods in science, because to me that's really kind of went at the heart of what the scientific method is really all about. And also what meta-analyses are about, like in medical sciences or psychology or statistics or any of those things. And so for example, like my field is psychology, and let's say you find a correlation between empathy and pro-social behavior or something like that. Well, don't just take that as like, open and shut case. Try 5 or 6 different methods of measuring empathy and pro-social behavior. And if you get the same correlation 5 or 6 times in a row with different methods, you can be a lot more confident that that result is something real and not just an happy phenomenon or something. So that's all I wanted to point out.
I'd like to give you an example of a successful and a failed replication. This is Gregor Mendel, who I have stated has done the best experiment ever. In his original paper, he says he got the same results with beans as well as pea plants. But in his second published paper, which almost nobody ever refers to, he did it with a plant called hawkweed, which doesn't work at all. It reproduces by apomixia, where all the characteristics come from the female plant. And he publishes this, and it's just awful. None of the results agree. And yet, of course, Mendel, by the turn of the 20th century, his results are accepted as the basis of genetics, and nobody paid any attention, as it turns out with good reason, to his second, or of course he never would have gotten tenure. Actually, he couldn't even pass the exam to be a high school teacher. He failed it twice. That tells you more about the exam than
Any other questions? Okay, so we're going to take a 15-minute coffee break, and we're going to reconvene at 15